You understand how language models work, but you've used AI tools that handle images as well. And images obviously aren't language, so how is it possible for a language model to understand an image? And the answer is that they don't. We have a different class of model called a vision language model with that capability. And so today we're going to be diving in and exploring how vision language models work in detail. And so I've got this purple square of an image, and I'm curious how our model is actually perceiving this thing. And uh, we can see that it's actually understanding our image in terms of language. And so I'd say that is the core idea, the core enabling factor of vision language models is that we are um, understanding images in linguistic terms, and then our language model can go on and do its thing. Let's get into the architecture here. So I've displayed our model, and we're using the Hugging Face Gemma 3 today as our example. And I want to show off three parts of this thing. So we have our vision tower, and then a multimodal projector, and then a language model. And so the key thing here is that we're actually dealing with two different models. We have a vision model, and then we have our normal language model, but then we have this multimodal projector in between. And so effectively, the multimodal projector's job is to translate the output of the image model into something that our language model can understand. So I made a couple of diagrams here to get a little more into the nuance here. So all of the mainstream vision language models today use vision transformers as their vision model. So we've got a diagram here outlining how data flows through that thing. And it all begins with just some processing steps up front. So if I have any image, it's going to get reshaped into some normalized form that our model knows how to handle. And so for our case, it's going to be 896 by 896. And then at that point, we can pass it to our vision transformer. And so in language modeling space, we can nicely tokenize things because there is kind of a set amount of vocabulary terms. Language is pretty discrete, whereas images are not. Images are continuous, and so it's not possible to map out the entire vocabulary of possible visual situations. And so our transformer expects tokens, and so the way that we essentially turn our image into tokens is through this patching step. So we pretty much slice up the image into a bunch of non-overlapping patches of equal size, and then we kind of flatten them out, and then they get their own embeddings. And so at this point, we're dealing with the representation of the image where we've effectively converted it into 4,096 different tokens. And then at this point, we just pass it through what's a pretty standard transformer. And one thing to note here, though, is that in normal language modeling, attention layers are all causal. And in this case, images, we allow them to see both ways. So that's bidirectional attention. And after our transformer has done a bunch of processing and stuff, we're left with our final hidden state. So that maintains the same shape as the tensor that went in, but it's obviously got a lot more enriched information. And this is effectively representative of what the image means in some way that the model has learned. So that's our vision transformer. And so that is like this vision model part of things. But then to kind of bring it into the broader context of the vision language model, I've got this other diagram. So let's start with text. So we know that to get text into our language model, we have to put it through our tokenizer. So that's a processing step. And then we're left with, in our examples today, we're going to be using batch size of 1. So we have one batch by in tokens, and then we can pass our in token IDs through our text embedding layer. And then at that point, we are left with one batch by in tokens with 2560 dimensions. And so that is the dimension model size for our Gemma 3 model. And I've got this little stop right here. So let's go over to images. And so that's that same processing step we just talked about. We're going to convert that thing into one image by 3 channels RGB by our 896 by 896. And then we can pass that to our vision transformer, which is going to output that 4096 tokens with this dimension. And so at this point, we want to pass that through the multimodal projector so that this thing can translate the output of our vision transformer into something that our language model can actually work with. And so that's what it does. Of note here is that we are compressing the number of tokens significantly. And then the dimension of these guys has to match what Gemma expects as well. And so once we have these 256 image tokens, we can now pass them into the language model because they've been translated into linguistic representation space. And so at that point, we can join up our text embeddings with our image embeddings. And then, so now we have our tensor that's the same shape, but in plus 256 tokens. So in text tokens and 256 image tokens. And then at this point, we just pass them to our normal text transformer. And so that's pretty interesting that at this point, the model doesn't actually care that these are image tokens at all. It just perceives of them as if they were any type of normal linguistic token. So a bunch of processing happens, and then we get an output out the other side of the same shape, but obviously more refined. And then at that point, we can pass that through our language head, and then we end up with this shape where we can actually predict the next token from that. Okay, so that is the core of how vision language models actually work. And something I'm interested in is trying to understand what those image tokens actually mean in the linguistic space. And so for that, we're going to be talking about this idea of unembedding, or effectively like finding the nearest vocabulary token to any embedding vector. And so we'll be doing that with images, but to kind of prove that it's a valid method, I want to talk about how it works for text tokens first. So pretty much I want to go from text to the embedding, and then once I have the embedding, I want to see if I can recover fully what that text was. And so I can run hello through my tokenizer, and then I can grab the embedding for that token. And so we're going to be dealing with that 2560 dimension vector that represents the hello token. And then at that point, you would normally run it through your transformer layers and process stuff, but we're just going to bypass that entirely and go straight to the language head. And then from there, we're just going to do our normal like softmax and grab the top 10 things just to visualize that. And we can see that the most likely token from this situation with a probability of 1 is hello. So we can fully recover that text from the embedding. So now let's talk about images. I have this method where effectively we're doing the same exact logic, but with images. So we're going to run the image through the Gemma 3 vision tower and then the multimodal projector. And so that is going to output 256 image tokens. And then we're going to do that unembed step for each of those 256 tokens. And then after that, I just want to kind of group by the tokens that occurred and see with what frequency they came up. And all of this is kind of just a rough attempt to understand what the AI is actually perceiving our image to be in its linguistic understanding. And so, like I say, since it is this like nearest neighbor grabbing vocabulary situation, it is lossy. Like um, for each token, the model will output an entire probability distribution, and we're describing the most likely thing. And so that's not a perfect way to understand the nuance of what the model is seeing a given token as, but it's a good proxy maybe. And so I've got more examples where we can look at progressively complicated things, and we can see that like with our black and white image, some of the tokens that pop up are obviously like semantically meaningful. So we do see like black and white and bicolor, dark, maybe like 0 and 1 or like some binary situation. Um, but notably, there's a lot of the like 74% of our 256 tokens are the. And so that brings us to the point I was talking about of um, grabbing the nearest neighbor makes sense. And with text tokens, it's a perfect mapping. But the reality of the image tokens is that they live in linguistic space, but they don't necessarily have to be exactly a given vocabulary token. So maybe think of it as like uh, an image token can kind of live between different vocabulary words. And I guess the um, is pretty common and therefore is probably pretty close to a lot of different places in our linguistic representation space. So for a more complicated image, I'm going to do the same thing and see similar results where we have a lot of those as well. But there is obviously some semantic stuff going on in here. So I think that is really cool that it's that there are tokens that we're reading and we can map them to language and see actually like relevant words like mountain or whatever else is in here. So that's pretty cool. And then this is an example where it is a snippet of code that I actually used in this demo. And it's kind of an interesting case because it's essentially like an OCR task. And if I run it, I was expecting that we would get a pretty clean mapping of like, okay, just kind of translate this image into the words that showed up. But that is absolutely not the case. So we got 106 distinct tokens from our unembedding thing. And there's a lot of weirdness in here. So a lot of Unicode characters I've looked, and a lot of these are like in foreign languages and just not what I would have expected at all, really. But it is interesting to see that this is how our model is like understanding an image that has a bunch of text. And to kind of take that idea a little further, got another example where we have our diagram that we talked about earlier. Um, and it's a similar situation here where there are things that are semantically obvious to me and some words that show up in here are recognizable in our output as well. But it just goes to show that like the the language model's understanding of images is very messy. It's very interesting. So all of that to say, they are just language models that learn to speak image. Really, the brilliance of vision language models is in that idea of a multimodal projector. So we have our foreign modality, the thing that is not language, in our case, images, and we have our image model and our language model, but they don't know how to talk to each other. And with that bridge, we can translate the visual information into the representation space that our language model already knows and understands. Um, and so this is really a powerful thing and makes them extremely useful by forcing our other modality into linguistic space. Then really we leverage what the language model is already so good at. It's able to reason, it's able to understand long context, it's able to do a lot of things. And um, really that idea stands. Like if we can just translate our problem into something that our language model can handle, something it knows how to work with, then we can really kind of use that language model as this like universal reasoning platform. So I think vision language models are super fascinating, and especially on the mechanistic interpretability side, trying to understand uh, what those image tokens actually represent in that language model space. Um, so this has been a fun video to make. If you're interested in this type of content, please like and subscribe. I will be making more of it. Thanks for watching.